We're going to talk about velocity and other rates of change. Mostly, we're going to talk about instantaneous rates of change. That's going to be a little bit weird, you'll see in a second. The answers are pretty easy to calculate if you're getting good at derivatives. Instantaneous rate of change should make you think of derivatives. But my goal here is also to get you to understand the meaning of what you're writing in addition to writing it. So we're going to imagine a set of cubes, one 1 foot long, another 2 feet long, 3 feet long, and 4 feet long. We're going to find the volumes of those cubes. If a side length is 1, the volume of that cube is 1 cubic foot. For a bigger cube with a side length of 2, that volume is 8 cubic feet. Can't quite fit on this guy. We'll just assume it has a side length of 3. The volume of that cube is 27 cubic feet. And one giant cube over here that barely fits, with a side length of 4, has a volume of 64 feet cubed. So you can imagine changing from one cube to the next, or it might work better if you think of, I don't know, a magical cartoon cube that we can expand. So we start off with a 1 foot long cube, and it grows to 2 feet long, grows to 3 feet long, grows to 4 feet long. So I'm going to ask a weird question, and that is, what's the rate of change of the volume from the 2 foot cube to the 3 foot cube? If you're able to answer that, you should also tell about the units you're going to use. So I want to highlight that we're talking about the rate of change of the volume, not just a change in the volume. Did not mean to mark that. A rate of change is going to be something measured with 2 units, like miles per hour, feet per minute, gallons per second. Now, rate of change at this point should also feel like slope. So if we're starting out looking at the 2 foot cube and then changing it to a 3 foot cube, most people can come up with the number 19. So from 8 to 27, you would have to add 19. And by the way, you would add 19 cubic feet. But that's not a rate. That's not a rate like miles an hour or feet per second. What else changed? Not only did we change from 8 to 27, we also changed from 2 to 3. So you can think of this as 19 over 1. That 19 was an increase in cubic feet, and the 1 was an increase in feet. So how else could we say that? For every 1 foot of side length added to the cube, we get an additional 19 cubic feet of volume. So we could say maybe the average rate of change from the 2 foot cube to the 3 foot cube is 19 cubic feet per foot. And what we mean by that is, as we said before, if we start at the 2 foot cube and end at the 3 foot cube, we add 1 foot of side length to the cube and end up with an additional 19 cubic feet of volume. If you're wondering if we should simplify feet cubed over feet, we shouldn't. That would look like feet squared. And we're talking about, in the numerator, a change in volume, and in the denominator, a change of side length. So we want to leave feet cubed over feet. So now, we're going to actually do some calculus. We don't have any particular cube. We have some cube, and it says Find the rate of change of the volume of a cube with respect to its side length s. In this class, in calculus, you should think rate of change, that sounds like slope. We're probably doing a derivative, and you are correct. Now, this isn't a great drawing, mostly because it's not labeled. And the problem does say we should call the side length s, so we'll write an s there. But I do want to point out that side length has to be a variable. It can't be a number. This couldn't be a side length of 2, because if the side length was 2, the volume couldn't change. And this, we're going to find the rate of change of the volume. So since volume is mentioned, I need an equation that involves volume. And side length is mentioned, and I know the side length of a cube, when it's raised to the third power, gives us the volume of that cube. So that's where I'm starting. We already said we were probably going to find the derivative, and we are. The derivative of s cubed is 3 times s squared. You might be thinking we're going to write v prime on the left, but we're not. We're going to use a more powerful notation. We're going to write dv over, not ds, ds. The reason we write that is dv over ds can be read as the rate of change of the volume with respect to the side length. The rate of change of the volume with respect to the side length is 3 times the side length squared. Well, that doesn't have a ton of meaning, so let's go back to our previous cube and sorry, I'm having trouble going back and forth, touching my screen. And we're going to say using s is equal to 2 feet. Okay, because we did talk about a 2-foot cube before. So what would we have there? dv over ds is equal to 3 times 2 squared, or 12. I wonder what units we're supposed to use. Well, let's think about this. dv is read as the change in volume. So on top, what would volume be measured in? A change in volume is cubic feet. And ds on the bottom is a change in side length. What would a change in side length be measured in? That would be linear feet. So, we're going to go back to these 3 cubes. And I want to point out, way back here, when we had the 2-foot cube changing to a 3-foot cube, we got an average rate of change of 19 cubic feet per foot. What we just calculated is the rate of change of the volume of the cube with respect to time, when the side length is 2 feet, is 12 cubic feet per foot. I'm sure you've noticed 19 and 12 are not equal. So what's going on? When we calculated this average rate of change, that was the entire time in between 2 and 3 foot long cubes. On average, we did 27 minus 8 over 3 minus 2. That 19 cubic feet per foot is kind of true the entire time. What about the 12 cubic feet per foot? When is that true? That number is true only when the side length is 2. That 12 cubic feet per foot you could think of as the rate at which the cube is growing. Let's think about, what if the side length was not 2 but something near 2, like 2.1 feet? Would dv over ds, the rate of change of the volume compared to the side length, still be 12 cubic feet per foot? Of course not. It would be a number slightly larger. And in fact, even if we used a side length of 2.01, let's squeeze in a 0. The rate of change of the volume with respect to the side length still would not be 12. That 12 is an instantaneous rate of change. Kind of like when you're driving down the road, this 12 is the speed your car is going at that instant, what you see on the speedometer. This 19 is an average, if we're using the car analogy, speed. Like you went 19 miles in 1 hour, but we didn't really know the speed in between. We just checked the endpoints of the interval. Let's do another example. How could a circle be growing? That seems a little bit odd. Normally we think of circles as just standing still. Well, maybe you drop a pebble into a pond and you see ripples going outwards from there. I think that's a great example of a circle growing, or the area of a circle growing. I'm going to get rid of all that, get back to my circle. Okay. And so the next question I like to ask is, what's the radius of the circle? It seems pretty obvious that we should be using this, but that's not true. It says we're going to find the rate of change of the area of a circle. And if we said the radius was 3 inches, the circle couldn't grow. The circle couldn't change. So we need a variable we'll call the radius length r for now. Whenever we're doing calculus, you have to think about what's always true and what's true only at an instant. If the circle is growing, how long is its radius? 3 inches. It's not very long, it's just 1 moment. So we have to use that 3 inches after we've done a derivative. Before we do a derivative, we need some sort of equation involving area of a circle and the radius of a circle. The area of a circle is pi times the radius squared. And we're talking about a rate of change in a calculus class. That's a derivative. The derivative of pi r squared is 2 pi r. You might be wondering how we got that. Don't worry about the pi. That's a constant multiplier. So all I thought of was the derivative of r squared. That's like the same as the derivative of x squared, 2r, and then we just multiply by pi. We're not going to write a prime. We're going to use a notation that says even more. dA over d r. The rate of change of the area with respect to the radius. Okay, so now that we've taken a derivative, we're talking about an instantaneous rate of change, and we can say, using the radius of 3. Then what would you have? The rate of change of the area with respect to the radius is, just substitute a 3 in there. 6 pi. Now I'm always stuck on units. What would a change in area be measured in for a circle like this? Well, we're talking about inches, so inches squared is going to be a change in area over a change in radius. That would be measured in inches. Let's see if we can explain what this means. So we got a rate of change of area of 6 pi inches squared per inch, which kind of means if we extended the radius by 1 inch, all this extra area added on would be 6 pi square inches. Now, of course, that's not quite true because we know this rate of change, 6 pi square inches per inch, is only true when the radius is exactly 3. If the radius was slightly more than 3, like 3.1, 3.2, we would have a different rate. This one's weird, and I'm going to try to go quick. Find the rate of change of the volume of a cylinder with constant height when its volume is 12 inches cubed. Actually, I'm going to pause there, and I'm going to make a new video of that one so I can take my time.